Well, hopefully you've not been too confused lately with this new idea of equilibrium, because it's going to get a lot worse. Just to warn you. I don't know, maybe it's not. If you can play the game, it's totally easy, but this thing's called the law of mass action. It's also just simply writing the equilibrium constant expression, or one way that we define it. And it goes like this. Well, in essence, P.S. We're going to break all the rules that we just taught you in the last unit of not to do this. But now in equilibrium, this is the rule to do this. To write some kind of ratio or some kind of number that describes the amount of products in relation to the amount of reactants. And indeed, the rule is just to take the amounts of products, C and D in this case, capital C, capital D, and the amounts of reactants, A and B, in the denominator, and raise them to the coefficient number power P and R, and J and M. So P and R and J and M are numbers, C and D and A and B are chemical species, and we just, concentrations there of chemical species. We just take the numbers and plug them in and do the math and find an answer. We may or may not know what that number means yet, but I'll tell you. The larger K is, the more it tends to favor the products. And the smaller K is, the more it tends to favor the reactants. Because think about it, if I have a whole bunch of C and D and a little bit of A and B, in some way I guess the reaction favors making C and D. And the constant will be large. And by large I mean larger than 1. And by larger than 1 I mean usually a lot larger than 1. Thousands, millions, something like that. So, also, you may remember these square brackets mean molar concentrations, molarity, moles per liter, but it's also quite, so that's called concentration or molarity, little c, or Kc, or Keq, equilibrium, the concentration constant. But you can turn it around if you're using gases in some kind of equilibrium situation. You can use pressures of gases, works equally as well. Although Kp and Kc aren't always the same. They might be the same, they might not be the same. Here's an equation we'll talk about. Probably not this video, but later. In any case, I take the pressure of C, pressure of gas C, the pressure of gas D, the pressure of gas A, the pressure of gas B, to the little p power, to the little r power, to the little j power, to the little m power, and we find the number. And again, if the constant comes out bigger than 1, we know we probably favor the reaction at this temperature. This particular equilibrium probably favors the formation of the products. Interesting. Let's do some numbers. Here's an equilibrium cartoon where I have H2 and Br2 in equilibrium with 2 HBr. So it looks like the H2 looks like this, and the Br2 looks like this, and the HBr looks like, and in this particular cartoon, if it's true that these particles move around really fast, bouncing into each other, once we reach an equilibrium situation, we have, if I count them, 9 units of this, and 1 unit of this, and 1 unit of that, and 9 squared is 81 over 1 times 1 is 1 is 81. So I suppose at this temperature, at the macroscopic level, in any case, I end up having a whole bunch more of this than this. Now, if there really were only 9 particles of HBr, 1 molecule of Br2 and 1 molecule of H2, then they still would be changing. We still would have occasionally this one reacting with this one to give 2 of these, or 2 of these colliding to give 1 of these and 1 of these. So I would still have some forwards and backwards on the particulate level. But in terms of the macroscopic concentrations, after reaching equilibrium, it seems like this number and these numbers aren't changing. Interesting. Another cartoon, 6 units of N2, 1, 2, 3, 4, 5, 6, 4 units of O2, 1, 2, 3, 4, 2 units of NO if I am indeed in an equilibrium situation. So macroscopically it looks like that these concentrations are not changing. But of course the particles are moving around, bouncing off of each other, and occasionally one of these reacts with one of these to give 2 of these, or 2 of these collide to give 1 of those and 1 of those. But that's on a particular level. So it would be more realistic to say 6 moles of this and 4 moles of this and 2 moles of this. Or if they're gases, 2 atmospheres of this, 4 atmospheres of this, 6 atmospheres of this. In any case, if you know the numbers at an equilibrium situation, you can find the value of the equilibrium constant. This one comes out smaller than 1, so what does that favor? Oh, yeah, if it's smaller than 1, that means this is smaller and that's bigger, this is smaller and that's bigger, this is smaller and that's bigger, and this is smaller and that's bigger. So if this is bigger, I favor the reactants as it's written from left to right. So, yeah. You can imagine these numbers changing. This could be smaller, this could be bigger, but the ratio of these numbers should still be 0.17 at this particular temperature. If KEQ is larger than 1, then the equilibrium favors the creation of the products. So here I have no products in the beginning, and it goes up and up and up and up and up. Looks like this is the concentration, and I have all reactant, and it goes down and down, 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 down. And so, yeah, favors the products. Large reverse rate. Oh, wait a second, I better read the. So it's definitely the products. Large reverse rate constants. So if the constant is bigger than 1, that means I favor the products. And if I favor the products, I favor the forward reaction. So the forward rate constant Kf would be large, not small. So it's definitely B. Yeah. Large reverse. Yep, that's all I have to say. That's the answer to that one. Here's some other based on, where'd it go? I know I had that. I'm losing my mind. Oh, it's right. H2 and Br2. I guess this is from another video I made recently. In any case, here's an H2 and I2 in equilibrium with 2HI. Initial concentrations, yada, yada, yada. Calculation, constant is 50. Oh, temperature. They give us the temperature, but we don't use it in the calculation if we know the concentration is measured at equilibrium. So in other words, doesn't matter where we start, we still end up at a constant of 50 at that particular temperature. If I were to warm the temperature up, well then that would change the equilibrium constant because it changes the rate constants forwards and backwards. But warmer or colder, it affects the equilibrium constant. But nothing else, it seems, regardless of the beginning concentrations, affects the equilibrium constant. Beginning concentrations certainly determine or predict the equilibrium concentrations, and we can get into that in a future video and in lecture, but not right now. Even though the initial concentrations and equilibrium concentrations of all species may vary all over the place, quote, the equilibrium constant for a particular temperature will stay the same unless you change the temperature. The rate of the forward will always be equal to the rate of the reverse when you've reached equilibrium. But that might take a few minutes or a few seconds at least. How about if you want to pause the video, you could practice writing the equilibrium constant expression, practice applying the law of mass action, as it's sometimes called, to these two balanced equations. Jeopardy music, pause the video, nobody's watching you right now, you can do it. Or be lazy, and here's the answer. Well, if the products go in the numerator, my HI goes upstairs and my H2 and I2 go downstairs. There's one of these and one of these and two of these, so that 2 goes up there. And if I knew the molar concentration of HI, I would square it. And I'd take the molar concentration of H2 and the molar concentration of I2 at this particular equilibrium. I could call that Kc as well. This one would be H2O in the top and NO in the top, O2 in the bottom, and NH3 in the bottom, and the 4 and the 5, oh my goodness, to the 6th power. So the molar concentrations, or take the pressures. If they are all gases, it's just as simple to use the pressures, the partial pressures that we learned of in Gen Chem 1 when we talked about gases, and raise those to the powers. Kp and Kc for this reaction would actually not be the same. They'd be close, but maybe in a future video we'll talk about how to figure Kp and Kc. Wait, did we just do that? We just did that. Yeah, I think we just did that. NO, H2O, O2, yeah, okay, NH4, yeah, no, what? I should delete that one from my, I think there's a boo-boo here. There's no NH4. Really, it's NH4 plus. Or maybe that's not even balanced. What in the world? I'm going to delete one of these pages. I'll delete the wrong one. Whichever one's wrong, I'll figure it out later. But the mass action expressions written correctly. What about this one? What's the multiple choice? What's the constant, the concentration constant, Kc or Keq, for this react? Didn't we just write that? Oh my goodness. Well, I'm not even going to tell you the answer then. You can figure it out. Sometimes thermochemists balance equations with fractions. And if that's the case, it's kind of weird, huh? 3/2 of a particle of Cl2, you can't have that, but you can have 3/2 of a mole, so 1.5 moles. So 1 mole of this reacts with 1.5 moles of this to give 1 mole of this in an equilibrium situation. What's the Kc or Keq for this? I said Kc because that's concentration. Little c is concentration. What is the answer? So I have one of these. This one's looking promising. PCl3 to the first power, phosphorus gas to the first power, Cl2 gas to the 3/2 power. So yeah, that would be kind of complicated on your calculator, but you could figure it out. If you were given this concentration, this concentration, this concentration, take this one to the 1.5 power, multiply it times this one, take that answer and divide it into this concentration. That's an exercise in, so the answer is C here, right? That's an exercise in using your calculator correctly. Thanks guys, and I'll see you soon.